You have a few videos on this, but how does a rocket engine work? You're wearing some of the instruction manuals, but for one type of it, like what's the fuel? What are the kind of types of different rockets that you can kind of give an overview?
Yeah. Ultimately, a rocket engine converts high pressure and heat into kinetic energy. Like that's the only real job of a rocket engine, is to take high pressure gas, high pressure gas, very energized. There's a lot of energy involved, and then literally turning that into molecules shooting in one direction, into kinetic energy. So, what you do basically, the simplest version of it is, of course, like famously a balloon. You take a balloon, you fill it up with air, you've got a pressure, you let go of it. Some of the air shoots out in a general direction-ish. You converted that pressure into kinetic energy. Now, if you start scaling that up, you can continue to do something like that. Like cold gas thruster would be kind of the most simple and easiest rocket engine to make, would be a cold gas thruster. And all that is you literally just take air, or specifically nitrogen, because it's a little bit more dense than all the others, or, and it's the majority of our atmosphere. It's more sparse. You can condense that down, sort in a really high pressure bottle, and then just literally shoot it through what's called a de-level nozzle, which is something that chokes the flow a little bit, gets it to be, takes it and gets it into supersonic speeds. Once it's at supersonic speed, you actually can't choke it down anymore. You'll just constrict the flow of mass flow. You'll constrict the airflow. So you actually go opposite. You start making it wider. And once it's already at supersonic speeds, if you expand it and make it wider, it actually gets faster and faster. So at first, when it's subsonic gas, you start shrinking, you constrict the flow, it's actually speeding up, just like, a highway. If you go from, or any of these examples, like a water hose, if you pinch it down and you want to flow the same amount of water from point A to point B through a smaller pipe, you can flow more water, or the same amount of water from point A to point B with a smaller pipe. It just has to go faster. Mm-hmm. So obviously you can constrict it, but at some point you actually get to a physical limitation, and that happens to be the speed of sound. Once it gets to the local speed of sound, you can then actually do the opposite. You actually expand it back out, and you're continuing to convert the pressure into velocity at that point, but it's now supersonic. And what's interesting is, while you're doing that, you're actually cooling it down too. Each bit of that pipe that you're making wider and wider and wider, you're cooling down. So the more heat energy you have to work with, the more work you can actually do. So at some point, a hot, high pressure rocket engine is the best source of, that's the ultimate amount of work you can do.
And the nozzle, so as you're saying, there's a bunch of different design options, but it's a critical part of this.
Yeah.
How you do that conversion. Which
it's basically like how much can you convert is really like the ultimate game. How much pressure and heat can we convert into thrust? Like that's really, at the end of the day, that's what a rocket engine is. So you have to have a powerful enough rocket engine to actually lift the rocket, and a rocket is mostly just fuel. It's like 90+% just the weight of fuel. So you just have to lift the fuel that's going to take it into orbit.
And that's the thing specifically for rockets. You're just saying generally rocket engines, but for the task of going to orbit, you're fighting gravity, Earth gravity, which is fundamentally different than moon gravity or Mars gravity.
Yeah.
Or like you said, traveling out into space. Earth has a pretty intense gravity to overcome.
We're lucky, because I think if it was 10% either way, like 10% harder, it'd be like, we could still do it. We'd still, with our current technology, we'd still be able to get stuff into orbit. Man, things like reusability and this, commercialization, the success that we've seen in the last 10 years, we'd just be on too thin of margins, I think. 10% easier, and we would have been like, it's just like totally different. It's so much easier. It's like this big, sliding scale, and 10% in either direction, we'd be either screwed or really happy, as far as getting into space. So it's just hard enough that things like fully reusable becomes very, very, very difficult. I think it's completely achievable. We have all the pieces to make it achievable. It does not disobey any laws of physics. It does not disobey there's no hard stops to it. It's just very, very, very hard. And so ultimately, like on Earth, for the first bit of launch, again, when the rocket's pointing straight up and the engines are pointing straight down, pointing end up, flaming end down, you're fighting gravity. And so that's kind of your biggest enemy outside of the Earth's atmosphere too.
So what kind of sources of fuel is there? So there's chemical rockets, liquid, solid gas, hybrid. There's electric. So what are the kinds of fuels we're talking about? What are oxidizers? What? Can you just explain your shirt? I guess.
Yeah.
The components of your shirt.
So really, I mean, fuels. There's kind of two terms. Well, you'll generally hear the word propellant being used. It's anything that is used to propel a spacecraft or used in a rocket engine. So you have to have, you can have a fuel. You have to have a fuel, you have to have an oxidizer, and you have to have a spark to actually get those things burning. And that's just a general law of like the universe. You have to have fuel, an oxidizer, and a spark. Now, some fuels will by themselves spark, like hypergolic fuels, but ultimately you're always left with some kind of fuel, oxidizer, and a spark. So the general ones used most often in rockets, liquid oxygen is kind of the king of, well, there's better oxidizers, but they're extremely, extremely hard to work with, like fluorine. But generally liquid oxygen, so you just chill oxygen down to its liquid state, minus 183 degrees Celsius. So it can be dense enough to store in tanks. It's 1,000 times more dense when it's in a liquid than it is as a gas. RP1, which is basically kerosene, is a very common fuel. Another common fuel nowadays is methane, liquid methane. Liquid hydrogen is another. It's the most efficient, potential for the most efficient, since it's one of the lightest molecules.
So I think, correct me if I'm wrong, but Falcon 9 uses kerosene, and then Starship uses methane, liquid methane?
Yep, for fuel. And they both use liquid oxygen for their oxidizer.
For the oxidizer, okay.
Yep. But then, if you get into hypergolics, you'll normally have nitrogen tetroxide, which is your oxidizer, and some form of hydrazine for your fuel. There's solid rocket propellants, like solid rocket boosters, and those are actually pre-mixed. Your oxidizer is inherently like baked, literally like kind of baked into the sludge of fuel.
So like for SpaceX, it's all chemical liquid fuels.
Yep.
So how many solid based fuels are there? Are they still being used today? Is there most rockets?
Yeah, and the United States really is the only ones that, I guess early on, because it was really just the Soviet Union versus the United States. The United States started to use solids pretty early on. They're simple and easy, but these days, like, you'll still see them kind of as traditionally like boosters, like they're used to just help get something off the ground or help give it a little extra boost. So the space shuttle famously had those two huge white solid rocket boosters attached to the orange fuel tank. Those are solid rocket propellants. Things like the Atlas V can have up to 5 smaller solid rocket boosters. There's very few rockets that use a pure, at least these days, that use a pure solid rocket motor for its first stage. There still are, especially in China, there's a lot of startup rocket companies that kind of use just missile technology. They might use there might just be a variant of an ICBM that just use solid rocket fuel because it is relatively easy to develop. Model rockets use solid rocket motors and stuff like that. So they're still around, but they're just not as elegant and not as used these days, I'd say.
So what are rocket engine cycles? I think getting more towards your shirt question. You have a really good video called that. A lot of your videos that are technical are just exceptionally well done. So I think you deserve all the props you get. Thank you for doing this work. Really, 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 really well done. So it's called Rocket Engine Cycles. How do you power a rocket engine? And you go through all the different options. Is there something you could say about open cycle, closed cycle, full flow, all the different variants that you can use words to explain?
Yeah, without all the pretty pictures.
Yeah, without the pretty pictures.
So ultimately, like we said, your ultimate goal is you want to get heat and pressure into an engine. So obviously at some point you can either make really thick tanks of your rocket. You can like get it so thick that you store the propellants in really, really high pressures. But obviously like that doesn't scale very well. At some point your rocket's so heavy you can't even leave the ground, or it's just so much of your mass is just literally the walls of the rocket. So at some point people realize, hey, we could actually just pump the fuels and the oxidizer into the engine at a high pressure and increase the pressure through a pump. Now obviously a pump's going to require energy. You have to get that energy from somewhere. And again, at some point, people were like, well, there's already rocket fuel here. We'll just use some of the energy from the rocket fuel to spin these pumps. So that would be considered like open cycle, closed cycle, full flow stage combustion cycle are ways to tap into the propellant. Actually, and then there's tap off expander cycle. All of them kind of do the same thing, but you end up at some point spinning a turbine. A turbine can take some of the heat energy and the pressure of an engine, and then that can be connected to a shaft to pumps, and those pumps can increase the pressure of the propellants and force it into the combustion chamber. Now, the difference between open cycle, closed cycle, full flow, all those is what happens after the gas has flown through the turbine. So after you've used the turbine and spun up the energy, spun up the engine, what happens to that gas? So in an open cycle engine, you basically have like a separate small rocket engine in a sense. It's a gas generator, they call it. And that will be used to create take a little, we'll say 10% of the propellant flowing to the engine. Instead, you reroute it to like a smaller rocket engine called the gas generator. You point that at your turbine, and that will spin your turbine up to, ridiculous speeds, 30,000 plus RPM. And then after it spins, it's wasted most of its energy, and it's just dumped overboard. That would be open cycle. You're not worrying about it after that point, but you are left with a lot of unburnt, unused fuel. A good amount of that fuel is just completely, and especially because the turbine, you have to keep it from melting. So you can't run it at like optimal ratios. Not necessarily stoichiometric. In a rocket engine, you actually don't want it to be near stoichiometric where you're releasing all the energy. You actually want to release, you actually want to be throwing out the lighter molecule so it can be shot out faster generally in the engine. So, but in order to have a turbine survive, you have to actually cool. You have to have the gas going through it. It can't be stupid hot, or else you're just going to melt your turbine. So they normally, especially in the open cycle, you just run it really fuel rich. So there's a lot of extra fuel being pumped into it that will keep the temperatures at a reasonable, temperature. So you end up with this like dark, sooty smoke pouring out of that gas generator. That's just unburnt fuel. It's just wasted fuel. It never got a chance to be used.
Oh, interesting.
Like in the combustion chamber. It's not being used to propel the rocket. It's just being used to cool down the propellant that's being used to spin the turbine, that's being used to spin the pumps to push a lot of propellant into the engine. So, it doesn't take too long before, you're a greedy rocket scientist being like, look at all this wasted propellant, all this potential energy that's just literally being spewed out the side of the rocket. So that's where the closed cycle comes in. So now you have to get that propellant, take it from basically what was being wasted through the turbine, and you're going to try pumping it back into the engine. Now, you don't literally just pump that gas that's, that gas into the engine, because it's actually way too low of pressure compared to the main combustion chamber. By that point, by the time it's gone through the turbine, it's lost most of its pressure and heat to the turbine. So if you tried pumping it into the engine, just taking that pipe and sticking it right into the combustion chamber, the much higher pressure, hotter combustion chamber would just go backwards, and it'd stall out the engine and blow up the engine and whatever, what have you. So what they actually do is they normally will send, there might be some variations of this, but the general concept is you actually flow all of your fuel or all of your oxidizer through the turbine. So that would be closed cycle. So there's fuel-rich closed cycle, which would be you're flowing all of the fuel through the turbine, or there's oxidizer closed cycle, which is where you're flowing all of the oxidizer that's going into the engine through the turbine. Now, the trick here is you have to have that turbine after it's done its work. So after it's taken some of the potential energy, some of the heat energy from, we're now calling it a pre-burner, by the way, instead of it being a gas generator, you now call that device that's creating pressure to spin the turbine. You're now calling that a pre-burner because it's just going to pre-burn some of your fuel or some of your oxidizer. The trick is that has to be, by the time it's gone through the turbine, it has to be higher pressure than the combustion chamber, because otherwise it's going to go backwards still. So you really have to get that pre-burner up to ridiculously high pressures, like at least 20% higher than your main combustion chamber. And these combustion chambers, we're talking about engines that are at, 200, 100 to 200, even in SpaceX's Raptor engine, up to 300 bar in the main combustion chamber. So that's, 4,500 PSI, basically. Insane amounts of pressure inside these combustion chambers. So your turbine has to be even above that, or your gas generator or your pre-burner, has to be higher pressure than that even in order to have the flow going the right direction through the engine. So now you'll have those closed cycles. You'll have fuel rich, you have oxidizer rich. The tricks now, you're starting to get, it's crazy. There's just so many compromises. Every little decision you have of like, oh, I did this. Now now crap, it's going to do this. For instance, fuel rich, if you ran kerosene, fuel rich, how I mentioned soot coming out of the gas generator. Well, if you run soot through your engine like that and had it go through your injectors, like back into the engine, it'll clog the pores of the injectors and it'll end up blowing up the engine. The soot itself is so damaging that you can't really run a fuel-rich kerosene engine.
What exactly is soot? So it's like fuel somehow mixed up with the smoke. Like what? I wonder what is it chemically? It's just some weird.
It's mostly just carbon. It's
Carbon.
mostly just carbon,
That dark smoke.
solid chunks of carbon, and it can cake up and just literally like,
Yeah.
it's like ash almost, like at some point, especially under those high pressures and high temperatures, it can physically build up and, turn into like stalagmites and stalactites of carbon, really hard, forged in a rocket engine carbon.
I wonder how you figure all that out too. It has to be experimentation. Some of that is chemistry, like theoretical, but like you're gonna have to build the thing at scale and actually test it.
Trial
and error.
There's
many decades of trial and error,
and many pieces of engines that you're trying to piece back together, going like, "What the hell happened here?"
Yeah, what happened?
Yeah.
Okay, so that's closed cycle. So how do we get to full flow?
So in either of those situations, you're still actually just having the opposite. So if you're fuel rich, all the fuel is going through the turbine, but only a tiny bit of oxygen is actually being put into that preburner to spin the pumps, and the rest of the oxygen is actually going through the pump, the primary pump, and straight into the combustion chamber. Now, full flow, the idea is you're going to actually preburn both your propellants. Both of your propellants are going to go through a preburner, and they're both going to end up spinning one of the pumps.
Mm-hmm.
So you'll have a fuel-rich preburner, and you're going to have an oxygen-rich preburner. Each one of those is going to get just, they're going to heat it up just enough and get it up to just enough pressure to spin up that turbine as fast as they need to do to get the pumps up to the right pressure, and still have enough pressure through the turbine to overcome the pressure inside the main combustion chamber. And they're both going to arrive, both your fuel and your oxidizer are going to arrive in the main combustion chamber as hot gases already. So what was liquid oxygen is now gaseous oxygen. What was liquid methane is now gaseous methane. And they're meeting in this combustion chamber at still ridiculously high pressures. Again, for SpaceX's Raptor engine, they're meeting at 300 bar. Insane amounts of pressure. And then they combust from there on. And because they're already a gas-gas interaction, they're happy to burn. They're ready to burn. They're ready to mingle, as opposed to having a gas-liquid interaction, which is what's a lot more normal. You'll have two different states of matter, and they just might not. They might take a little more coaxing to, what's that word?
Coaxing?
Coaxing?
That doesn't sound like that doesn't sound correct, right?
Coaxing.
Coaxing. Yeah.
Yeah?
All right.
I don't know. We'll cut that in post.
No, we'll have Morgan Freeman overdub us.
Yeah, each of us coaxing.
The fascinating thing is they're coaxed as gases in the combustion chamber.
That word? But yeah, they just take a little bit more. It takes more time in the combustion chamber to have a liquid and gas interaction like mixed together and unleash as much of their energy as you can before it exits the system.
Are some of the trade-offs here in terms of efficiency, which is most efficient, and then also complexity of the design and the engineering and the cost of the design and the engineering? Like, what are the different trade-offs between open cycle, closed cycle, and full flow?
Yeah, it's kind of like a what's the bears, the Goldilocks, it's like you kind of generally, the easiest is open cycle. Because you're just expelling the exhaust gas, the gas generator exhaust. You're not having to worry about it. You just spin up that thing as much as you need and deal with it, right? No big deal. Closed cycles offers 10 to 15% greater performance generally because you're not wasting that propellant. But it's complicated. It's a lot more complicated, especially if you're doing oxygen rich. Now you're having hot gaseous oxygen in your engine, which just generally wants to react with everything. It's just a recipe, like hot oxygen is just a recipe for things to catch on fire that shouldn't be on fire. So metals, under those conditions, lots of times will just spontaneously start burning. You'll actually turn your metal and it will now become fuel. You'll be engine rich before you know it because your hot oxygen
Nice.
is eating and using that engine as fuel, basically. So oxygen rich is generally very hard, but that is what the Soviet Union ended up doing with almost their entire line of engines was closed cycle oxygen rich. But, so those two are kind of generally hard, but offer great performance benefits over open cycle. But at the end of the day, full flow is by far it's the ultimate of all of them. It's the most difficult, but it also has the most potential to be the most efficient.
Starship, the Raptor 2, why is that engine using full flow?
Because it's the best. I mean, it's just physics wise, if you're trying to extract as much energy out of your propellants, there just isn't another cycle type that is better than it. But of course, it's very, very hard to develop. So far to date, the RD270 in the 60s was built. There is a powerhead demonstrator built in the United States in the 90s and early 2000s, I think, maybe just the early 2000s. That was just the power, just the pumps and the turbines and the preburners, no chamber, no nothing. That was a big deal. Only the United States took millions of dollars to just develop that. And then there's SpaceX's Raptor engine.
So you talked about the combustion chamber and how damn hot things get.
Mm-hmm.
High pressure, a lot of heat. How do you keep the thing cool? You have a great video on this too. How do you get it from what do you call it? Metal rich, engine rich.
How do you keep it
engine rich from like the metal from melting?
Well, one of the ways is to let it be engine rich. There's actually, you can use ablative cooling. You can literally make the walls thicker than you normally make it out of a material that will ablate away, that will kind of chip away and take some of the heat away with it. It's very, again, primitive. And it's actually what SpaceX first used on their first Merlin engines. They used ablative cooling. So it's basically a carbon nozzle, and you just let it get the inner layer of the engine was carbon, and you just let it get chewed away and eaten away. And that's just something you factor in. It's not very elegant, and it's definitely not reusable in that sense.
So there's probably really good models about like how it melts away, the rate at which it melts away to know what thickness.
Yeah.
But boy, that's dangerous.
I just
it's part of the design.
It seems so silly. So obviously you probably, wow. It's not the most elegant. And the problem too, your geometry physically is changing too, because as you're eroding the walls, now things like your expansion ratio or the ratio between your throat and the nozzle exit is changing.
Yeah.
Because the thickness, like the throat's diameter is actually, like everything is changing. So it's not great.
It might not be melting away uniformly. There could be some like weird pockets for aerodynamics stuff. There's just a bunch of chaos I
can't imagine having to like figure all that stuff out, honestly.
Yeah.
So the more elegant thing to do, there's a couple other things you can do, but the kind of the most common one, especially when we're dealing with liquid fueled rockets, is something called regeneratively cooling. And the idea is you basically just flow fuel or oxidizer through the walls of the nozzle and the chamber before they go through like into the injector or into the actual combustion chamber. Mm-hmm. By doing that, you're taking heat out of you're taking heat out of the metal of the walls and you're putting it into the propellant. So you're typically heating the propellant up, which is, remember when I said there's a gas interaction versus a liquid, like liquid gas. So lots of times, even if you pump them both at, as they, are both being pumped as liquids, by the time it goes through the walls of the chamber, lots of times one of them is phase changed into a gas. So now you do have that gas liquid interaction. That's because they're using the fuel or the oxidizer to cool the walls of the engine. So when you look at a rocket engine, although it looks like, a nice, beautifully uniform cylinder, smooth thing, there's oftentimes like the channels actually like milled into the walls that they run fuel through. And even though they're tiny, they can be like 2-3 millimeters thick, they'll actually still have a channel that goes down and U-turns and comes around and comes back.
Wow.
All the way down to the tip of the nozzle and everything. So it's just insane that,
Isn't that's pre-designed and that's like, so they design those channels.
Yeah.
There's probably some optimization there, like how the flow happens.
Well, especially because you're thinking about a conical thing or like a semi-conical thing where the area is getting smaller and smaller and smaller. You're flowing the same amount of propellant through it as you are down to the, what I mean? Like the propellant has to, so they have all these unique things like, sometimes different manifolds where they'll inject more or less fuel in certain areas. And
there must be like propellant simulation software because they surely can't like test this on actual physical.
Well, back in the day, they had to just build it.
Well, you mean back in the day, walked uphill in both ways. It was like, I mean, like anything back in the day before computers, where you like had like,
you just had to do it,
and like your simulation or modeling was like a sheet of paper where you're like calculating stuff.
Well, but
loosely
you can
estimating.
heat flux, like you can literally see how much energy and how much heat is inside the combustion chamber, how much, and that is a measurable thing even without a computer. Now, I'm not near smart enough to do any of this. Like, I've never tried measuring the heat flux of anything. I barely even know what that means. I'm just smart enough to regurgitate
lived, my
it.
friend. Then you haven't
So
lived.
but that is something that people would calculate, and they find out, okay, copper, does a better job of transferring the heat between the walls of it and into the propellant, blah, 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 compared to XYZ. So,
Materials people. I've met just in all walks of life, especially just through MIT, through everywhere, where there's some people are just like 100x smarter than anyone you've ever met at a particular thing. Like you mentioned copper. They'll know the heat dissipation through different materials. They'll understand that more than it's like, holy shit, it's possible for a human being to deeply understand a thing.
Dude, aerospace is full of that. You'll have people that are so niche in some thing that the average person has never even remotely thought of. Yet this person has done it 40,000 different ways in an environment, being like, well, we found out that if we turn it 4 degrees that way and add 4% niobium, things you're like, what is your life? And how do you know this?
And the funny thing about them, they usually don't think it's a big deal.
Yeah.
They're usually like, they're so nonchalant about it that if you don't actually, you have to know enough. You actually have to know quite a lot to appreciate how much more they know.
Yeah.
Because otherwise you won't even notice it. Because our popular culture doesn't celebrate the intricacies of scientific or engineering mastery, which is interesting. There's all these people that lurk in the shadows.
Oh, I know.
They're just geniuses.
Yes.
Like you'll have like the LeBrons who are like good at basketball, so we understand that they're good at basketball. They do this thing with the ball and the hoop, and they do like it really well, better than a lot of other people under pressure. We celebrate.
It's this big public spectacle.
Yeah,
look at how great they are. Yeah,
but like the people, at these aerospace companies at NASA, at SpaceX, the kind of stuff they're doing, just there's geniuses there, and it's actually really inspiring. I mean, I've interacted with a lot of brilliant people in the software world. And maybe because I don't deeply understand a lot of hardware stuff, materials engineering, mechanical engineering, those people seem like so much smarter. I mean, it's always like the grass is greener or whatever the expression is, but there's a depth of understanding that engineers have that do like mechanical engineering that's just awe-inspiring to me.
Well, not to get too I don't know what the word would be, introverted or something or whatever, but that's actually kind of the whole point of Everyday Astronaut. Like that's almost the whole point of what I do each year. From the beginning, I did a thing called the Astro Awards, trying to be like an award show, hoping to lift up and celebrate and shine a spotlight on the people that are actually doing the hard work, and try to treat them like the rock stars that they are, that we don't know about. And I think that's one of the things that for sure I think Elon definitely helped make spaceflight cool. Helped make that like a celebration thing where people are physically out cheering for rockets and science and space exploration. But I think that's just the beginning. I think like this should be a thing where the general public looks to these people as the coolest ones, as the coolest places to work, as the most important things. Sports are great and everything. I'm a big Formula One fan and things like that. But, at the same time, like we should be celebrating the people doing this crazy work, clocking in countless hours, just trying to figure out this one little thing that's going to help us further our understanding.
I mean, what's cooler than a giant thing with a really hot fire that goes boom and goes up into the air? I mean, like there's no, it's like, to me, like bridges are inspiring. It's like incredible architecture design, and like the humans are able to work against nature, build these gigantic metal things, but like rockets, with a tiny little humans on top of them, flying out into space. It's like it's the coolest possible thing. Everything comes together. All the different disciplines come together for the high stakes drama of riding that super powerful thing up away from the thing we call home, Earth. Exactly. It's like, it's so amazing.
Exactly.
So freaking amazing.
Well, I think that's kind of part of my like story arc, is I just used to be a huge car and motorcycle guy. Like I just loved, things that go fast and, are loud and go fast and make lots of power. And at the end of the day, like at some point you realize nothing goes faster and it's louder and makes more power than a
Yeah.
rocket. You know, and I think that's kind of where I eventually just ended up. You know, wound up there just because there is nothing cooler than that.
Yeah, that's the ultimate level of reach as a car guy, is to become a rocket guy.
Yeah, 100%. And at some point, some car guys literally become rocket guys and strap rockets to cars and try and break land speed records. You know, like it's the same universe here, and yeah.
So Elon, with your conversation with him on the Raptor 2, was talking about, or you were talking about, like there's an excessive amount of cooling to be on the safe side as you're developing the engine. What kind of cooling was that?
So that would be film cooling. So remember how a little bit ago we were talking about like keeping the turbine from melting? You can just run it off nominal, basically off, typically fuel rich. Just run more fuel through that so it's cool enough. You can actually do that locally, kind of in your engine, so that you can keep it. So imagine a combustion chamber, and the top of it's just a flat. Like imagine a shower head, and then you have the combustion chamber attached to it. The outer perimeter there, the part where the flame front would be touching the walls, you can actually have just more fuel injectors. So you're injecting locally a more fuel-rich zone along the entire nozzle, and that would be called film cooling. So it's less efficient though. Again, you're kind of wasting fuel. There's fuel that's running, and your mixture ratio is off, but only for a little portion of the big picture. So that's one of those compromises. Like you can do additional film cooling to make sure you're not melting your engine, but at the cost of performance usually. But you can also be smart and use film cooling. There's fun little clever tricks. For instance, you'll notice on the F1 engine that was on the Saturn V, the biggest rocket that had been built to date prior now to Starship. The F1 has this huge engines. There's 5 of them on the Saturn V, and you'll notice that the gas generator has a pipe that comes down, and then it actually splits off in a manifold and wraps around part of the nozzle. Mm-hmm. And that manifold takes the hot gas from the turbine, which is actually, it's not hot. It's actually cold gas compared to the combustion chamber. But it's, in human terms, you wouldn't want to put your hand in it. You'd not live. And it actually pipes that gas into the nozzle so that it creates a film cooling, an actual boundary layer of cooler gas against the hotter combustion chamber gas. So they're basically repurposing that gas that was normally wasted, and they pump it back into the engine and then into the nozzle, like kind of further down. So the trick there is it has to be far enough down that the pressure in the nozzle, because remember, as the nozzle gets bigger and bigger and bigger, the pressure is getting lower and lower, and the temperature is getting lower and lower. So you have to find this trade-off point where the pressure is lower than that gas from the turbine, mm-hmm. and then you pump it in, and it's cooler than the gas still is in the nozzle, and it can help not melt your nozzle. So you'll notice that the F1 is actually a good example of regen cooling. So the chamber walls, you can physically see the pipes actually on the F1 because it's so big, and they just literally used pipes and bent them, and you can see the coolant channels all the way up and down the engine until you get to that manifold. Then from there on, it just has what's called a nozzle extension, and it keeps going and going and going. And that section of nozzle is cooled by the film cooling of the gas generator.
The aerodynamics of cooler gas and the hot gas, because you have to have this kind of layer, right? Protective layer of cooler gas. Like understanding that obviously probably has to do in modern times. There's probably really good simulation of aerodynamics, and to do it in terms of pressure too, to make sure it's in the right place.
Yeah.
That doesn't go back up.
Go backwards. Exactly. Yeah. If they have that manifold even 6 inches too high on that nozzle, it's just going to go upwards, And pressure always wants to flow from high to low.
The number of options you have here that result in it going boom is very large.
Near infinity, yeah.
Especially because, you can't do a small model of it. Maybe you can. No, you can't.
It doesn't really scale very well.
No, you have to do the full testing, and that's why you have all the kind of that's why you have with Starship all the tests that you think, why would you need to do so many static fires and so many tests, and why is it failing so many times? Can't you get it right? But it's very tough to get it right.
Well, and when you're pushing the boundaries, you want to know where and how it's going to fail.
That's right.
So you can engineer around them. So that's a luxury that SpaceX does have with the scale of Raptor. They're building Raptor cheaper than probably almost any other engine, maybe besides some of their own, at least at that scale. than before. They're testing, I think since last March or last April, they've tested 1,000 Raptor, 1,000 engine fires, I guess, not just Raptors, but that's just an insane amount of data and an insane amount of edge cases to learn. Oh my God, we found out that we were actually slightly overspinning our turbine at this degree, and this frequency is harmonic at this blah, blah, blah. And all of a sudden realize it's rattling and, it did this. And then you can engineer around that. It's like it ultimately, I think Elon said something like high production rate solves many ills or something along those lines. And it's just true. If you have an insane amount of engines and an insane amount of data, an insane amount of failures to learn from, you just know your system inside and out. You know those margins. You know where the failure points are. You know how to engineer around them. And
that's how I approach dating. No, I'm just kidding.